Hello students, this is the second part in a two-part video series about probability. We're doing the elementary statistics week 5 curriculum here. We're going to be talking about Venn diagrams like these, sample spaces written out like these, a spectrum of possibilities or probabilities like these. Let's get into it. The first thing I'm going to talk about is the general addition rule. In the previous video, we talked about the addition rule where we add the two probabilities of the two events together to get the probability of both events at the same time, or E or F. But in this case, we're going to take into account what if the two events are not disjoint? What if there's overlap between the two events? I'm going to illustrate that using this picture. Suppose that a pair of dice are thrown. These are all the different possibilities, or these are all the different outcomes that could happen when two dice are thrown. E is the first die is a 2, and F is the sum of the dice is less than or equal to 5. In order to find the probability of E or F, you could either look at the sample space, this is the sample space here, and try to figure out how many of these match the two rules, or you could use the general addition rule. Pause the video and try to use the general addition rule and then come back to see if you did it right. All right, you can see that I circled all of the outcomes in event E in blue. That is 1, 2, 3, 4, 5, 6 different possible outcomes that the first die is a 2. 6 divided by 36 is the probability of event E happening. For the probability of event F, we're looking at 10 different outcomes for 5, 6, 7, 8, 9, 10. So that's 10 out of 36. The probability of E or F, I'm looking at all of the events that were circled, all of the outcomes that were circled, is 13 out of 36. There's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Remember, we're looking for anything in E or anything in F. But keep in mind, if we were to take probability of E and probability of F and add them together, I'd get 6 plus 10, which is 16 divided by 36. Why is E or F only 13 out of 36? Well, you can see right here that there are three different outcomes, I should say, that are excluded from being counted twice. This one, and this one. I don't want to count them twice because that's considering them to have happened twice, which they can't, or the probability of those outcomes happening twice, which doesn't happen. So here's how to use the addition rule in this case. We know that the probability of E or F is the probability of E plus the probability of F minus any double counting. We call this double counting when E and F happen simultaneously, or when there's overlap. So 6 out of 36, 10 out of 36, we figured that out already. We subtract out that 3 over 36 because, again, there are 3 overlapping cases here. So when we draw out the sample space, it's easy to find the overlapping cases. If you don't draw out the sample space, it's easy to use this formula instead. This is a formula that we will be using in class. All right, moving on. Using the complement rule is a little bit different. The complement rule deals with whether an event happens or whether the opposite of that event happens. Here's an example, or here's the definition rather. If S is the sample spaces of a probability and E is an event, the complement of E is everything that didn't happen from that event. So, for example, if I'm rolling a fair die, if I'm talking about the probability of rolling an odd number, that would be 1, 3, and 5. The complement of that event is 2, 4, and 6. Those are the things that couldn't happen under the regular event. Complement means the opposite, or sometimes I refer to this as the other guys. Here's the complement rule in picture form. The entire region is this rectangle. This is probability of everything that could possibly happen. The area of the region that's outside of the circle represents EC, and this C, of course, stands for complement. That's the complement of the event E. So E has all of the outcomes that are encompassed by event E, and EC, the complement of E, is all of the different outcomes that are not encompassed in event E. So we could also say that the probability of the complement of an event is equal to 1 minus the probability of that event happening. For example, according to the American Veterinary, Medical Association, 31.6% of American households own a dog. How cute. What is the probability that a randomly selected household does not own a dog? Well, it's the other guys. It's the rest of it. It's the leftovers. The probability of not owning a dog is equal to the probability of 1 minus the probability of owning a dog in the first place, because you either own a dog or do not own a dog. So 1 minus 0.316 is 0.684. So the probability is 0.684. You could also say that the percentage is 68.4%. All right, using probabilities and complements here, taking a look at the example, we have a probability distribution here on the right-hand side, the probability model, and it tells us that all of these different travel times are experienced for residents of Hartford County, Connecticut. For example, on the top here, it says less than 5 minutes, 24,358. That means 24,358 of the residents travel less than 5 minutes to get to work. So for for section A, it's fairly straightforward. What's the probability that a randomly selected resident has a travel time of 90 or more minutes? Well, it's literally on the table there. It's 4,895. We're dividing that by the total number of residents. In this case, we're adding all of these frequencies together to get 393,186. And we do 4,895 divided by 393,186. That's 0.012. So there is a 1.2% chance that a randomly selected resident will have a commute time of 90 or more minutes. Well, using the complements rule, how could we figure out the probability that a person does not have to travel 90 or more minutes? In other words, the probability of not 90 or more minutes. Using the complement rule, we could say, well, this probability, or these number of residents, these guys are all traveling 90 or more minutes. So the other guys have to all be added together and then divided by 393,186. Well, that's very cumbersome. I would have to do this one plus this one plus this one plus this one plus this one. That would be a little outrageous. There's an easier way to do it, and the easier way to do that is with the complement rule. On the next slide, it talks about the complement rule. The probability that a randomly selected resident has a commute time that is less than 90 minutes, well, that's easy. We'll take the probability of 90 minutes or more and subtract that from 1. So 0.988, in other words, 98.8% chance that a randomly selected resident of Hartford County, Connecticut, would have a commute time of less than 90 minutes. The next thing we have to talk about is independent events, something that students sometimes get confused with mutually exclusive events. Independent and mutually exclusive means something very different. I want to walk you through that now. Take a look at independent events here. Now, it says that two events are independent if one outcome or one occurrence does not affect another outcome or another occurrence. For example, if you're rolling 2 dice, the outcome of one die does not affect the outcome of another die. If you roll a 1 on one of them, there's still an equal percentage chance that it could get a 1 on the second one. Another example of that would be flipping a coin. If I flip a coin and get heads, there's not a greater or smaller probability of getting heads the second time or the third time or whatever. They are independent if that happens. However, dependent events are events in which one event's outcome affects another event's outcome. So, for example, if I'm looking at a deck of cards and there's 52 cards in the deck, I pick a card and it happens to be the ace of clubs. Well, that changes the probability of getting a card next, because now I'm not drawing out of a deck of 52, I'm drawing out of a deck of 51. So dependent would be like cards where I don't put the card back, a deck of cards, and independent would be like rolling a die or flipping a coin, something that one event doesn't affect another. All right, in these examples, you can see that drawing a card from a standard deck of 52 cards and then rolling a die, both of those individual events don't affect each other. So the event draw a heart and roll an even number. If I draw a heart from a deck, it's not going to change the number that is rolled on the die, and vice versa. So those are both independent. However, if I was drawing a heart and then trying to draw another heart, or draw a spade, for example, from the same deck without putting the card back, those would be dependent events. If 2 40-year-old women who live in the United States are randomly selected, woman 1 survives the year and woman 2 survives the year, that's independent because, well, the survival of one person does not necessarily affect the survival of another person. Since they're randomly selected from the United States, they could be from totally different places, so there's very little chance that one of their lives is going to affect another life. However, if 2 40-year-old women live in the same exact apartment complex, the events woman 1 survives the year and woman 2 survives the year are dependent. Because, for example, if the apartment complex, happens to have, elevated levels of lead in the water, or whether it happens to, burn down in a fire or something like that, all very maudlin ideas. But that would necessarily mean that both woman 1 and woman 2 are exposed to the same situations, so their probabilities, the probability of one is definitely going to affect the probability of the other. They're dependent events. Here's using the multiplication rule for independent events. You've probably seen this before. Well, let's get into it. If E and F can be proven to be independent events, in other words, one probability does not affect the other, then the probability of E and F is the probability of E times the probability of F. Let's see it in action here. The probability that a randomly selected female aged 60 years old will survive the year is 99.186%, according to the Vital Statistics report. This is an actuarial idea. The idea of giving life insurance to people is inextricably tied to the idea of trying to predict when somebody's going to die. I know it's a kind of a sad thing to think about when somebody passes away. We're just trying to use it as a probability tool here. The probability that a person survives, the first woman survives, and the second woman survives is going to be equal to the probability of the first times the probability of the second. We're able to use this because the survival of the first female is independent of the survival of the second female. So we're multiplying those two together and get 0.9838. It's still a very high chance. All right, manufacturer of exercise equipment knows that 10% of their products are defective. Seems pretty dangerous, doesn't it? They also know that 30% of their customers will actually use the equipment in the first year because a lot of people buy it in January and try to meet their New Year's resolution, but they don't do that. What proportion of the customers will actually make a valid warranty claim? Well, we need to calculate the probability of defective and used, which is equal to the probability of defective times the probability of used. Because whether or not it's defective, they could use it. And whether or not they use it, it could be defective. These are not dependent on each other. They're independent events. So multiply them together. So there is a 3% chance that the equipment is defective and also it is used in the first year after it is purchased. Moving on to the next slide here, the multiplication rule extends for independent events. For example, if we're trying to figure out the probability of multiple events happening, E, F, G, H, I, whatever, are independent, then we can multiply all of their individual probabilities together to calculate the probability of all of them happening at the same time. Here's the example here. We go back to that statistic from earlier, the 99.186%. And we're now looking for the probability of 4 randomly selected 60-year-old females surviving the year. So all we have to do is multiply all those together. And as you can see, as we add on or multiply on multiple different survivors, our probability is going to go down. If we were trying to figure out the probability of 10 women surviving or 100 women surviving, the probability would go down because necessarily as you go further and further and as you include more and more probabilities in this situation, there's a higher likelihood that one of these people is likely to die. All right, at least probabilities, it's a trick of language, especially a trick of English to talk about at least or at most. It's a little difficult for students to parse sometimes, but at least or at most have very specific meanings in math. The probability that a randomly selected female is surviving, the same statistic as before. What's the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Well, at least one means either 1 or 2 or 3 or 4 or 5. So what we could do is we take this probability and multiply it by itself. Well, I guess it would be how many times? 499 times? That seems a little silly. So what we're going to do instead is we're going to abuse this rule. This is the complements rule that we learned about before. The probability that at least one person dies is equal to 1 minus the probability that nobody dies. Well, the probability that nobody dies is all of these numbers multiplied together, 0.99186 to the 500th power. This is the probability that all the women survive. It's fairly low. Because if you talk about, 500 randomly selected women, the probability is that this year one of them is going to die, unfortunately. If we subtract that from 1, we get 0.9832, which means that there's a 98.32% chance that at least one of these women is going to pass away during the course of the year. All right, moving on from sad subjects, let's talk about the rules of probability. All of these rules will be given to you on the formula sheet, the ones that are pertinent, so I wouldn't worry too much about that. Counting techniques. Let's talk about how problems are solved here. One thing that I have to remind you of is factorial. Factorial is when I take a number and multiply it by all the numbers beneath it, all the integers beneath it, I should say. So this is called n factorial, or as I like to call it, n. Get it? Because it's an exclamation point. Another thing that I have to remind you of is combination. Combination is an arrangement without regard to order. In other words, the order is not important. So, if I wanted to ask you a mathematical question about combinations, I would be using this formula. This formula is n factorial divided by r factorial, n minus r factorial, where n is the number of objects and r is the number of objects that I want to select. So, determining the value of 9C3, well, pause the video, try to figure it out, and then see if you got it right. All right, here's how this works. How many different combinations of 3 objects can be made from a total of 9? The answer is 84 once you put all these into the calculator. And again, in future weeks, I'm going to be showing you a way to put this into the calculator fairly easily. Let's take a look at a real-world example. The United States Senate has 100 members. How many ways can 4 members be randomly selected to attend a luncheon at the White House? Pause the video and try this one out. All right, here's your answer. N is equal to 100, R is equal to 4, and I use my formula for that. I do a little algebra trickery here, but you can just use your calculator for this. I'm able to eliminate 96 from top and bottom and get 3,921,000. All right, this was the second video in the two-part video series about probability. Good luck studying.